Hello and welcome to Crazy Math Productions. Today we're finishing up our unit on exponential functions, on exponential expressions. Today we're looking at some growth and decay and looking at the difference between those families. So C is the starting amount. You can think of it, it's almost like, as far as linearity goes, the starting point, almost like y-intercept. R is the rate of increase or decrease. T is the time period, usually in years. And the growth factor is either going to be 1 plus r, or it's going to be a growth factor that's actually a decay, 1 minus r. If you take the number 1 and multiply it by itself, doesn't matter how many times, you're going to end up with just the number 1. If you take a number just smaller than 1 and multiply it by itself several times, you notice that it's going to slowly but surely start to get smaller. The more times you do this, then the smaller it's going to get. If you take a number that's slightly larger than 1, 1 and 1/10, 1 and 1/10 to the 4th power, that's going to give you 1 and 4,641 10,000ths. And so as you go through, if it's just bigger than 1, then it's going to continually get bigger. If it's just smaller than 1, then it's going to continually get smaller, or decay. Of course, getting bigger, that is growth. So you can see that it's all in relation to that all-important number 1. So now we're going to look at some examples, see if it's growth decay, growth or decay model, and we're going to say the rate of increase or decrease. So this one, it's larger than 1, so this is exponential growth. And it's in relation to the number 1. It's larger than the number 1. How much more so? Well, 1 and 5/10 minus 1 is 5/10. If we make that into a percentage, the rate is going to be 50%. And that's pretty much it. We're just identifying to which family it belongs and the rate at which that's happening. Okay, again, just looking at our growth factor or decay factor. This is smaller than 1, so this is exponential decay. If you multiply 99 hundredths by itself over and over and over and over, it's going to get smaller and smaller and smaller, down to almost 0. So this is exponential decay. Now how much smaller? If I take 1 and subtract 99 hundredths, I'll get 1/100th. And it's like if you have a dollar, 99 cents gives you 1 cent. And so if you make that into a percentage, that's going to be 1%. So that's my rate of decay. All right, on this one, don't be fooled. We're still looking at the factor that has an exponent here. So that's the 1 and 5/100ths. And this is exponential growth because it's larger than 1. So it's larger than 1. By how much? Well, if we take that and subtract by 1, that's going to be 5/100ths. If we convert that into a percentage, that's going to be 5%. That's my rate of growth, or my rate of increase. And last but not least, we have a fraction here. Still the same basic idea. It's 5/5 would be 1, so 4/5 would be less than 1. This is going to be exponential decay, because again, it's less than the number 1. How much more? How much less than the number 1? Well, 1 minus 4/5 would yield 1/5. As a decimal, that would be 20 hundredths. Move the decimal over, and that's 20%. So just convert to a decimal and give a percentage. So exponential decay and a decrease of 20%. And we want to write an exponential decay model for each situation that answer the questions associated. Between 1970 and 2000, the number of farms in the U.S. decreased by about 2.1% each year. In 1970, there were about 4 million farms. Estimate the number of farms in 2000. Now, we're going to start off with the starting point. Now, it says 1970. That seems to be the beginning date stamp that they give us. 4 million farms. Now, I can't just put 4 and say it's in millions. I'm actually going to go ahead and give the number 4 million. Now, I could say it's in millions, but we're going to go ahead and give the full number here. Now, it's decreased. We're talking about exponential. So exponential decay, we're going to do 1 minus. Now, I can't put 2 1/10 here. I'm going to have to convert that to a decimal, move it 2 places to the left, and we have 21 thousandths. We're going to raise that to the t power. This is my exponential decay model. That's the general and generic model. They also want number of farms in 2000, so I want to estimate that. Now, relate from 1970, that's my starting point, and the year 2000, that's 30 years. So I'm going to plug in a 30 for the t. And so we can plug this into the calculator. You could do it by hand, probably not the best idea though. All right, and we end up with 2,116,122. Now it's probably not really necessary to round to the nearest tenth of a farm. We'll go to the nearest farm. And here we have it. Now this is just an estimation, but we say about 2.1 million farms. So in 2000, there should be about, you could just say 2.1 million. We'll go ahead and give the full number, 2,116,122 farms. And since this is just an estimation, that's why I put that word in, about, in the sentence. Okay, from 1990 to 2000, the enrollment at Smallville High School decreased by about 3% a year. In 1990, the school had 1,800 students. Estimate the number of students enrolled at Smallville in 1997. Again, we're going to get our general model here. Y equals our starting point in 1990 seems to be the beginning year. They had 1,800 students, so that's going to be my C value. Now the growth or decay factor here is going to be determined. They tell us again that it's decreasing, decreased by about 3%. So we're going to say 1 minus instead of 1 plus. 3%, so 300ths as a decimal. And we're going to go ahead and raise it to the t power. That's going to give me my general model. I could plug in any year from, let's see, about 1 to 10, and this should work because my date range, this is telling me where the model will be successful for our estimation. Now, estimate the number of students in 1997. Well, we're going to figure out how many years from our starting date this is. 1997 minus 1990 gives me 7 years. So y equals 1,800, and the 1 minus 300ths to the 7th power. So that gives me, do on the calculator, and that is about, well, I'll tell you what, it's going to give me 1,454 students to the nearest student. Again, this is just an estimate. And we do need to give a general idea to the reader as to what this should really be. So we're going to say in 1997, there will be about 1,454 students. Okay, last but not least, in 2001 you purchased a computer for $1,800. The value of the computer depreciates by 29% a year. Estimate the value of the computer in 2003. Those computers do tend to go down very quickly in value. Okay, so in 2001, that seems to be the starting point here. So y equals $1,800. That's my starting point. It has depreciated, in other words, gone down in value. So we're going to do 1 minus whatever the percentage is. Now, to convert that to a decimal, we move it twice to the left, 29 hundredths. And we're just going to say to the t power, excuse me, I've written this very well here. So y equals 1,800 onto 1 minus 29 hundredths to the t power. That's my general model. Now I want to be a little more specific. The value in 2003, I should be able to subtract these 2 years, and we'll have y equals 1,800 onto 1 minus 29 hundredths to the second power. That will give me my estimate. And we end up with 907 and 38 hundredths. Now, since we're dealing with dollar value here, then this will be very acceptable. That works for the cents. So the computer will be worth about $907.38. Of course, if it were worth $850, that would be well within the range here, $950, somewhere in that range. But we're just giving an estimate of the value. That concludes our unit on exponents, exponential expressions, exponential functions, exponential growth and decay. Thank you so much for watching, and thank you for watching Crazy Math Productions.